Morning, everyone. Welcome to the talk. My name is Guang Yang. I'm from Jet.com. We are a startup online shopping company, e-commerce, founded at 2014. We were acquired by Walmart at 2016. I joined Jet at 2015, and along the journey, I've been working on search, recommendation, and supply chain optimization. Today, I bring you the work I accomplished with my colleagues, Matthew Mu, on this using machine learning approach to the shipping box design. So shipping box design, what do we mean by design, right? It's definitely not some artwork I draw. Everyone here, I suppose you have been shopped online, right? For me, as a customer, online shopping is kind of like a magic. You sitting at home in front of your computer, using your phone, using a tablet. There are hundreds or thousands of products. You find what you like, you put it in a cart, and you click, place the order, and 2 or 3 days later, boom, there is a proper package in front of the door, and exactly what you want, right? Magic. So what happened in those 2 or 3 days? What happened in between? When you talk with our associate at the fulfill center, you will see that when the customers placing the order, we'll receive some signals in the warehouse. We know the customer ID, we know the order ID, we know the product they look for, and where to find those, and we know the box, right? They have to pick a box at the beginning of the pick path and to get the product, because the warehouse, the fulfill center is so large, it's 10s or 20s of the Walmart supercenter. So you have to get those boxes. But the box here, and then package ship it to the customer. So, but take a moment and think about it. Who decides what box to put here, right? Each of the pallets put one side of the box. That's either, let's say, 10 by 8 by 7. You can put thousands of boxes on the pallet, but it have to be exact same size. So how these sizes are being determined, right? And that's what we are doing, right? That's what we call design. As a planner or as an analyst talking with the managers in the fulfillment center, we know that there are millions of orders being placed on tens of millions of inventory products we have every day. And each order actually requires some kind of like unique box size to be packed perfectly if you want to minimize the overall shipping cost. But in reality, you only can store at most, say, 15 to 30 different box sizes in your warehouse. Otherwise, if you have hundreds of thousands of different box sizes, you are associated a loss in finding those boxes. So how strategy to select those assortment of K boxes, let's say K equal to 18, from thousands of feasible boxes, right? Such as it's minimized over shipping cost. That we call design. It's a quite challenging problem, right? Yeah, it is. So take an overview, millions of products, and the millions of orders placed on it, right? You have to know your inventories, you have to know each product, their size, and also you need to know the shopping behavior. Some product is popular, some product is a tail product, it's been ordered once a year. And the goal is to minimize the shipping cost right? What we are doing here is that from those thousands of feasible boxes, select the best 18, right? This thousand of feasible box came from the business requirement. Let's say we always have the length greater or equal to the depth, greater or equal to the height for the box. You can have a box, let's say, as small as 8 times 6 times 5, as large as 13.6 times 28 times 24. So in between, you can increment the size by inch or by half inch or by quarter inch. If you increment by inch, it's roughly 3 to 4 thousandths. If you increase by quarter inch, that's the minimum you can get. You roughly have more than tens of thousands of boxes. And in the transportation logic, you can actually find that the price of shipping is determined by the box size, their weight, the dim weight factor, and the zones. So some of the case that some big box is actually cheaper than the smaller one because it's in the middle range. So you want to remove some of those. So at the end, let's say we have 6,000 available box, and we want to find this 18. Of course, what we propose is a data-driven approach to get those boxes, whereas traditionally, we rely on the domain expertise that been in the field for 10 or 20 years, who knows the inventories, who knows the customer shopping behaviors. But here we show that how we using the data-driven approach. The key ideas in our analysis is to view each of the box as a point in an imaginary box space and formulate the problem prescriptively as a classing problem, as a k-medoid classing problem, where at the end, when you find those medoids, it's actually a point and it's representing a box that gives you those assortment of, say, 18 boxes. Let's write it down. So this is a formula we get. And now the question is, where are the Wj and the Cij, right? The Wj is the weight of each point, right, in the formulation. And it measures the box economic values, its single values contribution to the problem. And Cij is the distance between those points, which measures the cost in substitution one box using the other when it's not available. And here, because the asymmetry of this box, you often have the Cij not equal to the Cgi. That's why, because it's generalized version of the weighted k-medoid classing problem. So the question is how we define and measure this Wj and the distance Cij. So Wj, we model it to reflect the box relevancy to your inventory, to your customer shopping behaviors, right? Essentially, we measure it descriptively by the economic value of contribution. You can think about it as the volume of the item is being packed by using this box when you have all the boxes available, when you have the 6,000 boxes available. That's when you have everything available, this is the best box for this set of order, right? And we discounted in a way that to penalize the large box. So if we have this rho equal to 0, it's exactly the volume is packed. If rho equal to 1, it's the utilization rate of when you're using that box to pack those orders in this ideal case. And the rho between 0 and 1 is kind of like a balance, a trade-off between those. And we assume it as tuning factor, and then we try to find it when we're doing the experimentations. Okay. As a side talk is that when we're doing this, we're actually packing you as on a 4D dimension, not only the 3D physical dimensions, but also we have this weight constraint. And we have to pack millions of orders into thousands of boxes in a very fast way because we need to pack it several times when we're tuning the parameters. So we need to be super fast. So we developed this and open source this package, GBP, that can not only pack an order of 20 or even hundreds of items into thousands of boxes in milliseconds, but it's also handle the order split. Say, for this order of 20 items, you want this 15 in a box, let's say 15 by 12 by 10, and this 5 item on a box of 10 by 8 by 7. And it's very efficient, means that it achieves 1% optimality when you compare it to the mixed integer problems solved by the groupies, but it's 1,000 times faster, hundreds of 1,000 times faster. So at the end, what we got is that for each of the box, so here we using the inch incremental, so we get around 4,000, and this total volume packed, this total box volume by using this box. And here simply we're taking the rho equal to 1 to give a demonstration, and Wj you get. So it's roughly from 0.6 to 0.8. And come back, we defined the Wj. Now, what is a Cij? The Cij is kind of reflect when you have this box J in the ideal case, right? You have all the box, the orders being packed, and when it's not available and you want to using another box I to replace it, what is the extra cost you have to basically to pay, right? And of course, we can do it by simply unpacking those orders packed by box J and pack it to the box I, but you have to do it quadratically. You have to do every pair and twice because the asymmetry by the order packing by box I is different by the order packing by box J. So we do some case studies, and eventually we propose using this analytic solution to get it. So we divide it for each of the column, like say the box for the box J, right, to 3 parts. One is a box I, which is dominant box J. That means all 3 dimensions of box I is greater or equal to each of the dimensions of box J, so that you know the orders being packed to box J can definitely be packed to box I with some sacrifice on the utilization rate. And Sj is a neighborhood of box J, so that you know it's roughly can pack, but you have some uncertainties. So we give this extra penalties alpha here to count for that uncertainties. And the Tj actually is a set of boxes that being dominated or say outside of the neighborhoods of the box box J, so that you know it's roughly couldn't being packed. If it's being dominated, then definitely it won't. And you give the cost of 0 because we want to minimize the lowest. The lower the Cij, the best. And as an example, if you're replacing this 10 by 10 by 10 by itself, it will be -1. That's the lowest you can get. If you replace by someone dominated, let's say 15 by 10 by 10, you get the -0.67. Actually here, define the Cij in this way is easier for theoretical development. It's more straightforward to think the I1 plus Cij as the loss of efficiency. For example, if you replace by yourself, 1 plus -1 is -1. 1 plus -1 is 0. So you don't have any loss, right? That's the best case. If you replace by this 15 by 10 by 10, you basically lost 33%. That's 1 plus a -67. Because you know it can be packed in 10 by 10 by 10, right? Those top 5 10 by 10 by 10 is kind of like the loss of the space. So that you get. And here, the 14 by 12 by 8 is not only you lost some space, but you have some uncertainty. So we give some penalties, so it's even have a smaller, higher score. So that's not ideal as replacing by the 15 by 10 by 10. So defining this way, we have both Wj and the Cij being defined. And now we can do the optimization. We propose a EM-based algorithm and a gradient-based algorithm. And we find that when k greater or equal to 10, in terms of the FS you get is roughly similar in the performance. But the gradient approach definitely runs much faster. And also, based on the Hauser's 1978, we have this constant factor approximation to the optimal solution. So we have some worst case guarantees. So here we just, in our paper, we just show this gradient approach. So in summary, the workflow is that we view each of the box as a point in the space. We estimate using a Wj to representing a single box its contribution to the packing when you have all the boxes available. And then we define this economic substitution score, Cij, to represent each of the box, its capabilities to replacing the other boxes when the other box is not available in the packing. And then we solve this generalized weighted k-medoid problem using this EM or gradient approach. And in practice, what we are doing is that we take tens of days of orders from history, and which is across different dates of the week, across different seasonalities to account for the change in our catalog in the winter and the summer, and the change in the shopping behavior, some holidays. And we divide it into the training set, the validation set, and the testing set. On the training set, we pack it. And for each of the parameter set, right, we have the row running from the 0.25, 0.5, 0.75, and 1.0, which is when we define the Wj, the discount factor for the box volume, and the delta, which defines the neighborhood of the box, and the size of the neighborhood, and alpha, which defines the penalties you're given when you have the uncertainties. Both delta and alpha running from 0, 1, 2, 3, and 4. There's 100 set of the parameters. For each set of parameters after the packing on the training set, you can get a set of 18 boxes. And you can run those 18 boxes on your validation set. And you can compare it with your historical, your log in your system. And you can compare the utilization rate, compare the number of boxes you use. And for this set of parameters, when rho equal to 0.5, delta equal to 4, and alpha equal to 3, we see that the improvement is highest. We have certified a reduction in the number of boxes. So roughly 10% of the improvement in the return rates. And then we combine both of the training and the validation sets and then packing it using this set of parameters, getting the final 18 boxes. 18 boxes you have, right? Assortment. This should be very close to the ones you get before using the same set of parameters. And then run it on your testing data set, which is as a prediction on when you deploy it, what you expect to get in the systems. And what we see is that it's actually better than the current expertise. This is kind of like a combine of several experimentations we did for Jet for Walmart. And we normalize the human expert, the ones we designed in the system, as to the utilization of 50%, and the number of boxes 1.0 is being normalized. And we see that our proposal often give you roughly 10% increase and slightly reduction in the number of boxes. We also compare a naive approach where you have box of, say, 555 and 666, 777, so on and so forth, so that you have all those cubic box, right? You can see that if you do that way, you will have only 36%. That means human expertise do have a lot of knowledge acquired. That's almost 30% increase in the utilization rate. But still, we can improve by using this data-driven approach. And also, this is one exact case where we have 27 boxes in the systems, and we starting from the 15, we see it's better than starting to get better than the 27, and at the end we're running from 15 to 27, we see a consistent increase in the performance because of the greedy approach. And here at the end we take the number of 18 boxes, because as lower the number of boxes, it's easier in terms of the efficiency when the associate running in the warehouse. So at the end we see 10% of box retention rates and slightly reduction in the number of boxes. And also what we happy to see is that this improvement is consistent across the dates of the year and across the fulfillment center, and the improvement is roughly the same. So there's no bias in the systems. And in summary, I would say this is an innovative application of the optimization in the field. We haven't seen anything similar being discussed in this field. And also, we have proposed some of the innovative analytics, the packing. We have published our methodologies. We have open sourced our solvers to the packing, to the k-medoids, EM-based and classing problems, so that people can quickly reproduce what we had. And it's have high inferential. We're starting to implement it at Jet first, and then it's quickly influenced on the whole Walmart family, including Walmart.com, Walmart US stores, Sam's Club, and Walmart Canada. And at this moment, we are actually working again with Sam's Club, the supply chain team, that's revisiting this box design because they recently changed their catalog. They see some difference in their customer shopping behaviors, and it's the time that they renew their contract with the third-party, the box suppliers. So it's a good time to revisit annually. And actually, in the process, we talked a lot with the supply chain managers. We talked with the procurement team. And the downstream from the supply chain is a transportation team. They actually sent us an email says that, congratulations, we see that because of the new set of box, we see about 20 million annual reduction in our transportation costs. A majority is from the transportation logistics. Some is from the saving on the box, on the air pillows, because you improve the utilization rate, you're using less papers, less air pillows inside the box. So it's beneficial to the environment. And here is some source link to the paper and to the package we develop. And I would say it is a quite enjoyable journey when you're working with outside of the team. And this is a high visible project, and we receive a lot of good comments from our leaderships. So I show you some of the comments they gave to us. Endorsement from our leadership.
Hello, judges. My name is John Yan. I'm the VP of Analytics at Jet.com, a subsidiary of Walmart.
Hello, judges. This is Nate Faust. I'm the head of supply chain here at Walmart eCommerce, one of the co-founders of Jet.
So hello, judges. This is Mark Laurie. I'm the president and CEO of Walmart's e-commerce business, which includes Jet.
Guangyang has been in my team for the last 4 years, and Matthew for the last 2 years. I have been always impressed by the work they delivered. For this project, we worked with the operation team to design the box assortment using the data-driven approach. This revolutionized the transportation logic and also improved the customer shopping experience.
And really would like to recognize and thank Guang and Matthew for the work that they did on completely revamping our box selection process for our fulfillment centers, which has led to a significant impact to our customer experience as well as the costs of delivering packages to customers.
And I'd like to say how impressed I've been with the work that's been done by Wang and Matthew on this shipping box project. It has really created a step change for us and for the customer. Not only has it reduced costs, but it's been a lot more efficient, it's been more environmentally friendly.
We have an exceptionally strong culture here within Walmart US e-commerce of operations and data science partnering together to drive value for our customers and value for our business. And this was a phenomenal example of that in action.
This is definitely the best work I've ever seen.
That was
Thank you.
incredible.
And it's really a great example of using data-driven approach to design and thinking.
Thank you.